So up until now, most of my projects have been relatively small. So when you have a smaller project, you can buy utility at like 480 volts. That will come in off the street, and then you can step that down as you need to get your 208 and 120 receptacle power. However, when you get to a certain size, like say you're providing power for a whole campus, well, the amount of power that you need cannot be provided at 480 volts from the utility. Instead, they will sell you primary service essentially, and that's like medium voltage. You can get it at like 13.8 kV or even 69 kV. So one of my projects, we're basically got 69 kV coming in, and there's a switch yard that steps it down to 13.8. From there, we distribute to every single one of the buildings in the campus, and then inside of each building there's a substation. So a substation essentially takes your 13.8 kV power, steps it down to 480, and distributes that within the building. That substation is a primary switch, a transformer, and a distribution. So it's a fascinating piece of equipment, and you can actually double end it. You can make it extra reliable, and no matter how certain things fail, you can actually still have power at a building, depending on how you put that whole system together. So today I want to go over what a substation is, the different components of a substation, and how you can configure it, like, just single standard normal substation, or you can double end it for extra reliability. So I'm going to go over all that today. I'm going to show you a single line diagram, a floor plan, and some pictures of what it all looks like. So let's get started. Okay, so let's just start off with what it looks like. Right here I have a picture of a standard substation, unit substation that's on a skid. So basically you could buy something like this from a vendor. I think this one might be Eaton. Yeah, so this one's Eaton, and it's essentially a medium voltage switch with a transformer and a distribution section. And all of this gets shipped to you on a skid that you can slide onto, inside of a utility room, or you can put on a super skid or something like that. All right, so for functionality, a single line diagram is the best way to illustrate how power comes in, how it gets switched, and how it goes out to your loads. So over here at this substation diagram, you can see that we're bringing in power at 13.8 kV. We have a primary side protection, and in this case, it's a normally closed switch with a fuse. This is a cast coil transformer that is going to be stepping down the power. So a transformer for a substation typically has a couple ratings. So you'll have the standard ambient air, AA for ambient air, at 80 degrees Celsius. So that's kind of like your normal operating conditions. And that'll be rated, in this case, at 1000 kVA. So if your transformer is just running day to day, this is the rating that it can handle. Now, if you need to push the limits of your transformer, let's say you just have a lot of extra loads for some reason, or sometimes if you have a double ended and one of the transformer fails, all your power goes in a single side, you'll start using these extra ratings. So 115 degrees Celsius ambient air is kind of like the next step that it can handle. And beyond that, you can have 115 C forced air. So forced air, basically you install a fan on your transformer to help cool it. And with that extra cooling capacity, you get some more capacity out of your transformer. So it kind of usually goes 80C to 115C is a 15% increase. And then if you slap a fan on it, you can get 33% on top of this rating. So essentially it's 1150 times 1.33, and that's how you get 1530. This is kind of like as max as you want to go, like future load plus your highest peak single-ended kind of deal. So I'll get more into that later when I show you a double-ended substation. All right, so after your voltage comes in, you step it down to 480 volts. You need a secondary protection for your transformer, so that's what this is. And then after your secondary breaker, you can feed it to your bus within the substation. That is your distribution section. So this bus is rated at 2500 amps. I guess I really only need 2000, but this bus is 2500. And then from here, we have draw out breakers, which you can tell by these little stabs. So this stab is like the receiving end that you plug into the bus, and then this is your breaker that you can draw out. So the whole unit kind of pulls out, and it's basically like a big cube. So these draw breakers are used to provide power to your like switchboards, your eyeline panels, or like your motor control centers. You would take substation power to something else that'll distribute it down to like the panel or breaker size. Rarely do you ever put a piece of equipment directly onto a substation. Sometimes maybe like if a chiller is really big, then you would run a chiller directly to a substation. But unless that thing is like, I think 1,200 ton chiller or something like that, that's what ended up going to a substation. If it's anything smaller than that, you typically might take it to a motor control center or a like mechanical panel. But anyway, so this is like the most basic substation that really you could use. You have a single feed coming in, you step it down, and you send it out. Okay, so now let's look at a double-ended substation. And basically what it is taking two substations and putting them together with a tiebreaker in the middle. So it looks like this, where you have your, I think this is square D, HVL. So HVL compartment, medium voltage. Your medium feeder, your primary one comes in here, and then your primary two goes over there. So you can see that there's a medium voltage section. Your transformer, it's a little bit hidden in this picture, but this is what it looks like on the other side. That's your transformer. And then the center is your entire feeder section. And then right here in the middle, you can see that it's a tie breaker. So this tie typically operates open so that this section is powered by this transformer over here, and then the right section is powered by the right transformer. So let me go over to the single line, and then I can show you how this functions. You can kind of see that if you just, to zoom in on the one half, it looks like a regular substation. You got your primary, your transformer, your secondary breaker, and then your distribution. Then you have your automatic transfer tie in the middle, and the other half of the substation. So what normally happens is that this tie remains open. So under normal functionality, each half of the substation works independently of each other. All right, so now with a double-ended substation, let's say one of your feeders to your double-ended substation drops out. Somebody was digging in the parking lot and they knocked it out. Or even a transformer fails. So if you look at the single line, half of this, let's say, this is side A and this is side B. Let's say side B just gets knocked out. No power comes in, the transformer is non-functioning, and these feeders down here don't see any power. Well, the system will now know that you can open this secondary breaker to kind of disconnect side B because it's not useful to you, and close this this tie breaker right here. So if you close the tie breaker, guess what? Bus A and bus B are now all together in one single bus. And that bus can be fed by this transformer. So this transformer obviously needs to be sized appropriately so that you can pick up the whole load. So if you have it sized correctly and you can do that, you can pick up all the load on one transformer. That is a fully redundant double-ended substation. That means that, no matter what you do, you can still pick up all the load. If you don't size it correctly, let's say you need, you need 2,000 kVA. Well, if you lose a transformer, you're not going to be able to pick up all the load off of a single side. So it's not a fully redundant substation. You'll have to shed some of your load in order to do that. So for reliability purposes, generally people like to size it so that under normal operating conditions, when your tie is open, each side is running at 50% capacity or less of your ADC ambient air rating. Then if you need to pick up the whole substation, then let's say, the other transformer drops out, you close the tie, and all of your feeders are running off of one transformer, this can run at 100% at ADC ambient air. And then you can push it a little bit if you need to and go up to 115 C ambient air. So that's kind of like your best design scenario. Then it's more reliable because then you don't have to rely on your last setting, which is a forced air using a fan. The fan may never run for like years, and all of a sudden, if you need it and it doesn't kick on, you're not getting that rating. So I like to design to 50% of your ADC AA. Then if you need a single N, you shouldn't exceed 150 CAA. And if you have future spare capacity that needs to go on, or something adds onto the system for future that needs to get picked up, well, that's when you rely on your 150C forced air setting. But the beauty of this is that you can have a facility that remains functional even if you lose a primary service or you lose a transformer. You can close the tie and the buses can shift their loads back and forth automatically without any downtime. All right, so now that we kind of understand how they work, let's look at a floor plan to see how we can arrange these pieces of equipment. This is a Revit family that's been passed around the company. I don't really like to use it because it's nice in that everything stays together. You got your medium, your primary side, your transformer, your secondary, and your tie. But like, let's say I add, I don't know, slot 2, I can put it here. And, oh yeah, okay, so slot 1, there we go. All right, so there's slot 1 and slot 2. Look at it. There's some errors in here. Looks like feeder 3 tag sticks out. So it's okay, but I generally don't use it. So instead, I actually use the switchgear family, and then I make sure that the dimensions are accurate to what I can pick from the catalog that I'm trying to select. So I like to build it out piece by piece, mainly because like I have different requirements depending on like where I want to tie, or if I want 2 primary side for switching or whatever. So this is kind of your standard substation. You got your primary, you have your transformer, your secondary breaker, and then your feeders. You have feeder 1, 2, and 3. Each one of these can typically hold 3 to 4 breakers per stack. I generally don't ever use more than 3, and then I leave the 4th one as a space or spare. So I guess if you were to look at it in that regards, each feeder can give you 3 breakers, so this is like 9 breakers that you can use. And then you can put a future in for future. The dotted line is your clearance area, so I have a clearance on the front and the rear, plus actually I have 6 feet above the family as well. So if you want to look at it like this, jump over to 3D view, you can see, okay, so that's the old, or not really old, that's the single substation family that I don't use. And then this is the piece by piece one. So you can see I have the top clearance, the front, and the rear clearance. That way I make sure that I have enough clearance around the entire substation and nothing runs overhead like a ductwork or, fire sprinkler or whatever. Anyway, so that's your normal substation. If you come down here to the double-ended one, you can see that's obviously much longer, and we have a primary on either end on the outside. Then as you work your way in, you have your transformer, your secondary breaker, and then the whole middle section is your feeder with a tie smack in the center. Sometimes you might need a tie and like a remote I/O cabinet. So if you need to, control breakers remotely from a master PLC, then that kind of goes near the tie as well. This lineup is really simple. It's great because, like you saw in the picture, if we go back to this double-ended, it's like a very neat lineup. You can walk down the whole thing. You can try to follow it. It's left, it's right. It's pretty simple. There's no exposed busways or conduits overhead to tie the 2 substations together. However, you can't always design it like this because these can get pretty long. So some of these are like 45 feet, 60 feet if you have a lot of feeder sections. And depending on your architecture, they may just laugh at you if you ask for a 60-foot long room. So some of the creative ways you can get around this is to kind of break your substation in half and have like 2 tie breakers on, a tiebreaker on each side. So what it looks like is this. If you were to just, so up here, if you were to just take this, snap it in half, and then put it next to each other, you can see that this is still a double-ended substation with a busway overhead that ties the 2 systems together. So in this arrangement, the substations will be facing each other. So this is the front side, this is the front side, and then the tiebreaker, usually just one of them is the one that switches, and then the other one is just lugs. Like you have busway that just goes right into, that ties into the bus of the substation. Sometimes you can have 2 breakers and then one just stays closed the whole time, and then the other one is the automatic one that switches. So while you can arrange the substation to be like this with a tie at the end to put them together, I actually wouldn't recommend this as much, simply because you don't have future expandable space. So like here, you can't add more feeder sections afterwards if you need to in the future. So if you're going to break it apart, why don't you do something like this? You have again, two substations, but instead of the tie being at the end, you can put it after the secondary breaker. So the power normally comes in here and it will just feed down to the feeders. Then if you were to lose a section, well, you can say shut off this secondary breaker and then close this tie. Then all of a sudden, all of this is picked up on one transformer while maintaining the ability to add future sections if you need to. So this is pretty flexible, and I really enjoy using this layout a lot. You can also sometimes not even have to put it across from each other. Like sometimes we had instances where it had to be like, jagged or on different floors even. It's not the best way to do it, but sometimes when you're painted in a corner, you do the best you can, and you can use this as a very flexible option. There was actually even a time where we had to split the transformer away from the substation feeder section, simply because it was like really hard to get the transformer inside the building. So we had the medium voltage go up to the transformer on the roof, and then we had busways feeding the step down voltage down into the penthouse area for where the distribution was. So it kind of looked like this, where the transformer was pulled out. We needed an auxiliary section because the bus ducts couldn't actually connect to the same cabinet as the secondary breaker, so it needed an auxiliary section. And then from there we dropped down to another auxiliary section which fed the rest of the distribution feeder section, and the tie was down there. So this was it's still technically a substation, because you still have, your medium voltage, you're stepping down your feeder, but it wasn't like a unit substation. We ordered it piece by piece and we put it together, and it was called a substation. So you can get pretty creative with it. Substations are very flexible, they're reliable, you can switch them in so many different ways. Like what I showed you here was tying on the secondary side, but you can even bring two feeders on the primary side and then have like two fuse disconnects up there. You can switch between the two on the primary side. So the disadvantage of that is that if the transformer fails, you're kind of out of luck. But if you have double-ended, double-switched primary, I've seen that even, where both ends have two feeds, you have to lose a lot in order for the building to be without power for an extended period of time. Here, actually, I have this pulled up. It was a project that never got built. We designed it in the concept, and then it was too expensive, and then they just never went with it. But anyways, we have two medium voltage feeders coming in. There was actually a switchover that we did on the primary side, so that the feeders can actually hit both ends of the substation. So if one feeder ran out, we can actually feed both ends of the substation and keep the whole thing running before we had to even close the tie. This is a crazy bonus cut, but anyways, we have two feeders coming in, we have a switchover, a double-ended substation with two tie breakers, and then the two tie breakers went into diesel rotary UPSs. Actually, I think we downsized to one. Yeah, it used to be two per building, which was nuts. But we come off of the center tap of the substation to a diesel rotary UPS for the entire building. So what that means is that the entire building is on UPS power, and UPS power is non-interruptible. So a generator power is different. Like when you lose normal power and the generator kicks on, it takes a little bit. Like you have to wait 10 seconds and then your life safety kicks on, and then 10 seconds after that, something else, goes on to generator. A diesel rotary UPS, the UPS, it's a flywheel. So your flywheel's spinning, you lose power, the flywheel's still spinning, and it's providing power via clutch and an alternator. Fascinating piece of equipment. But the building never sees that delay while the generator is starting up, because the UPS is bridging the gap for the entire freaking building. So that's what this is. This is a diesel rotary UPS that feeds your switchgear, I think, or we said switchboard here. So we had a switchboard after the rotary UPS that feeds all the production line equipment. So this building couldn't be down. Like, you lose power for 5 seconds and they basically say, yep, there goes $2 million. So they are willing to invest a lot of money into this infrastructure. Well, willing, but not willing enough. When we gave them the design to price it, they couldn't stomach the cost. But anyways, the power was so reliable that you had to have like 7 things fail in order for the switchboard to suffer any power interruption. Well, I guess short of a branch circuit being cut, but that's irrelevant. The switchboard had a 99.9999% uptime or reliability, because we also had campus generators feeding this on the medium voltage level. Really cool stuff, but I'll dig into that another day. All right, so that's my little tangent there, but that's my summary of a substation. What it is, the parts that it has, how you can arrange it in different configurations, what it looks like on the floor plan, how you can kind of break it apart, do different layouts with it and still be a very effective substation. I find substations to be a little more interesting than like an I-line panel board or your branch circuiting. You can do so much with it, and it's just a complicated piece of equipment that most people don't get to learn, because you're mostly working downstream. You're just hooking up receptacles, you're just hooking up equipment, and you don't really know what's powering your switchboard way up here. If you want to know about more exotic things like this diesel rotary UPS here, let me know in the comments below. I might just go ahead and try to explain that through some of their diagrams, some of the pictures, and I don't know, we'll have a ball. Anyways, hope you learned something. Thanks for watching, and I'll see you guys next time. Bye.